So last time we were looking at this parametric function, which was sine of pi over 2t and cosine of pi over 2t for x and y. And we were given this function, we wanted to sketch the graph, and we said we want to do that by looking at the covariation, how x varies as t varies, and how y varies as t varies. So we said, let t go from 0 to 1. Like this. And then what will x do and what will y do? So as t went from 0 to 1, we see that x would go from 0 to 1 also, right? Because when t is 0, you have sine of 0. And when t is 1, you have sine of pi over 2. And then when cosine, or when t goes from 0 to 1, cosine would go from 1 to 0. And remember, when we graph these parametric functions, we're graphing x and y together, and t is kind of invisible or is behind the scenes. And so here's t equals 0 up here at our point 0, 1, x equals 0, y equals 1. And then as t increases from 0 to 1, see, I might get the wrong one here. Let's try this one. There we go. So then as t increases, got to turn it on. There we go. And so as t increases from 0 to 1, x increases from 0 to 1, but y decreases from 1 to 0. And putting that all together, that looks like this, right? That x starting from here, that x coordinate is increasing from 0 to 1. You're just thinking about the x coordinate of these points. And the y coordinate starts at 1, ends at 0, so the y coordinate decreases to 0. And then we can continue to construct that table. T goes from, say, 1 to 2, 2 to 3, 3 to 4, and looking at how x and y changes. And I think we saw that it creates the unit circle. So here's t going from 1 to 2, and then t going from 2 to 3, and then t going from 3 to 4, and the corresponding changes in x and y to create the unit circle. Okay, so what is the equation of x and y for the unit circle? So how would we write the unit circle in terms of just x and y and not t?
X squared plus y squared equals 1.
Yeah, good. All right, so we know we get the unit circle. And we see that that's being generated parametrically by this parametric function, but it's also a set of points x squared plus y squared equals 1. So if they're both the same set of points, then mathematically they should be equivalent. So right? So if they're generating the same set of points, then the math should show us that these are equivalent expressions. So the key to showing that those are equivalent is the Pythagorean identity. And so for these parametric circles and ellipses, this is going to be the key, really key element to the algebra behind the ellipses and circles. So what is the Pythagorean identity? It says sine squared of any angle, so it can be any argument, plus cosine squared, just as long as it's the exact same argument, equals 1, right? So you've heard, you know, the sine squared plus cosine squared equals 1. And that works as long as the arguments of sine and cosine that you're using are identical. If you have a different argument, meaning a different thing that cosine or sine is operating on, then it won't work. But as long as these are exactly the same, you'll always have this relationship as true. And it's really just the Pythagorean theorem, right? Because we know cosine is the x-coordinate. Sine is the y-coordinate. And if it's the unit circle, it's 1. Okay, so what do we have? So we can apply the Pythagorean identity to this. If we have sine of pi over 2t and cosine of pi over 2t, those have the same argument. Then we can set up the Pythagorean identity, and this will be true, will it not? Because our argument for sine and cosine are the same. But what is sine pi over 2t? What is sine of pi over 2t?
1.
No, it changes. It's a function, right? Takes on many values because st takes on many values. But in our function, what is sine of pi over 2t? X, right? It's x in this particular function. So sine of pi over 2 squared is the same as x squared. And cosine pi over 2t is y. So we can write the Pythagorean identity because we have sine and cosine with the same argument. So sine squared plus cosine squared equals 1. But then we know that sine of pi over 2t is x. So this whole thing is x squared. Cosine of pi over 2t is y, so this is y squared. So there it is. This is showing that the equation for the unit circle is mathematically equivalent to this parametric function, which is giving us the unit circle. Okay, does that make sense? Any questions on that?
Sorry, you said that the parametric function is the same as the unit circle equation? Is that what you said?
Yeah, right. When we graph that's what we just did. We graph the parametric function, right? We graph this blue circle. And we said
Okay,
as t went from 0 to 1, we got this first quarter, and as t went from 1 to 2, and then 2 to 3, and 3 to 4, and it gave us the unit circle.
Okay, good. That makes sense. Thanks.
But we know that also the unit circle has the equation x squared plus y squared equals 1. And so then this, using the Pythagorean identity, that bridges the gap between our parametric function, it's expressed in the unit circle, and the x squared plus y squared equals 1 expressed in the unit circle. Okay, and so the parametric function has something that this x squared plus y squared equals 1 equation does not. I think we mentioned this last time also. What is it that the parametric function has in terms of the graph that just the plain x squared plus y squared equals 1 equation of the circle does not have?
Direction.
Right. So the parametric function has direction as t increases. Those points are generated in a certain direction, where this is just kind of like, you know, a smattering of points all at once, right? It's just like you get all the points at once. There's no real direction associated with this equation. But with the parametric function, we have this direction, and it's counterclockwise. Sorry, clockwise. For this particular function, it generates the unit circle clockwise, as you see it happening right now. As down here you see t increasing. Okay, let's look at another example. Any other questions on this example? Okay, so let's see here. So let's look at this one. So here, x is 3 cosine pi t. And y equals 2 sine pi t. Okay, so we want to sketch this. And we're going to use our covariation approach. Covariation means how does x change as t changes? How does y change as t changes, etc. So t, you can take t from 0 to 1. And let's just do that much and see what happens here. So as t goes from 0 to 1, what does x do? So x will start at, if we plug in 0 for t, we're going to get cosine of 0, which is 1, and then times 3 is 3. When we plug in t equals 1, we're going to get cosine of pi, which is -1, and then times 3 is -3. But what happened in the middle there? So we could say 3 to -3, but it's kind of like that's like a big, for this particular function, that's like kind of a large range of t, and we want to make sure we see what's going on in the middle too. So let's, what about y? So when t is 0, we get 0. When t is 1, we get sine of pi. Sine of pi is also 0. So here's y is kind of a better example of how we're taking too large of a range of t, or a change of t, because y just shows us it goes from 0 to 0, right? As t goes from 0 to 1. Sine of 0 is 0, sine of 1 is 0. So what should we do instead? So this is kind of like, well, what's that? We really need to see how y is changing, not just the start and ending points. Like in this case, then we don't know what happened in the middle. So how can we change our approach here to kind of rectify that?
Instead of showing the progression of t from 0 to 1, maybe try t equals 0 to t and half.
Yeah, let's take a smaller ranges of t, and we can kind of see that 1/2 would be good, because then we'd be going from 0 to pi halves, and that'd be like a quarter of a cycle, and that would be better. So let's just go ahead and change this to 1/2, and then we have x going from, so cosine is pi, so when we put in 1/2, we get cosine of pi over 2 times 3 is 3, and then but then at 1/2 we get cosine of pi over 2. Cosine of pi over 2 is 0. And sine of pi over 2 is 1, so 1 times 2 is 2. So this is going to be a better way to do this. Rather than using t ranges from 0 to whole numbers, we'll do half. So 1/2 to 1, and 1 to 3/2, and 3/2 to 2, and that will be a full cycle. So that would get us all the way to 2 pi, and that's a full cycle of both these functions. Okay, so what does cosine do when the argument goes from pi over 2 to pi? Let's go from 0 to?
0 to negative.
Yeah, -1, but then times 3 is -3. And then sine from pi over 2 to pi. So sine of pi over 2 is 1. That'll make 2. And then sine of pi is 0. Back on the... And so we'll go back to 0 with this. And then we'll be going from cosine of pi to 3 pi over 2. That's the x-coordinate, right? That's the x-coordinate. And so you can work this out looking at the unit circle, or you could do individual graphs. So individual graphs, this would be cosine. This would be sine. Right now we're in the third quarter of the cycle. And so what does cosine do? It goes from -1 back to 0, but then that multiplied by 3, so that's going to be -3 back to 0. Or you can make this actually 3. Make this graph 3 cosine and 2 sine. So in the third quarter, sine goes from 0 to -2. And then in the fourth quarter, cosine goes from 0 back up to 3. Looking at the graph there. And then sine goes from -2 back to 0. Okay, so here we go. So when t is 0, we've got the point 30. Zoom out one time here. So x is going to go from 3 to 0. So imagine x going from 3 to 0. At the same time, y is going from 0 to 2. So what's that going to look like? So start at this point, 3, 0, and x is going to decrease to 0 while y increases to 2. So then we'll be at the point 0, 2. So can you imagine it'll be something like this. That's x decreasing from 3 to 0 while y increases from 0 to 2. Okay? And then in the next, we're going to have x is going to continue to decrease to -3. So imagine x decreasing to -3 while y decreases from 2 to 0. So we're going to end there. And both coordinates are going to decrease, right? X from 0 to -3, y from 2 down to 0. And then similarly, we could keep going like that. Now x increases from -3 to 0 as y continues to decrease down to -2. And then finally, x increases from 0 to 3, and y increases from -2 to 0. So that now they're both increasing in the last quarter of the cycle. Okay, so what is this? What is this that we got? We got the unit circle?
Ellipses.
Okay, so now we have a different radius in the x and y direction, right? So like in the x direction, it's like a radius kind of a 3. The y direction, a radius of 2. And so it's no longer a circle, but then this is an ellipse. And so if it's an ellipse, we should be able to transform the parametric function into an equation of x and y for that ellipse, right? So there is a, what is the equation of an ellipse in x and y? Does anybody remember?
Is it like x minus 1 squared? Oh, no. Oh, okay.
Yeah, it would
Sorry.
be, so yeah, it would be x minus something squared if it had a different center. So we can do that.
Oh, okay.
So if it has a center other than the origin, it would be like x minus x center squared over the x radius squared, and then plus y minus y center over the y radius squared equals 1. So if you remember that, if you don't, that's okay. So this is an ellipse that has center xc, yc. And then it has a radius in the x direction of what I'm calling r sub x, and a radius in the y direction what I'm calling r sub y. And so if this is truly an ellipse, then it should be equivalent to an equation of an ellipse like this, in x and y, without t anymore, right? Just an equation of x and y, not a parametric function. So what's the bridge? How do we get to that? So what are we going to do? What's the bridge to get from this parametric function of cosine and sine to an equation of x and y that doesn't have t in it anymore? What was our bridge? What was the key idea, that bridge that we worked on in the last problem? That's that key link between parametric functions of cosine and sine.
Is it the Pythagorean identity?
Yeah, Pythagorean identity. So we want to write the Pythagorean identity, but this time we want to write it with the argument being pi t. So we're going to write the Pythagorean identity using pi t, because that's our argument. So what would that be? So we know it's sine squared plus cosine squared equals 1, but sine of what now?
Sine pi t.
Yeah, sine of pi t squared plus cosine of pi t squared equals 1. So that's a true statement. By the Pythagorean identity, we have the same argument for sine and cosine, so we can write sine squared plus cosine squared equals 1. Well, but what is sine pi t? And for our function here, what is sine pi t?
It's y.
Y over 2.
Y over 2, right? Y over 2. Here's my sine pi t. So sine pi t would be equal to y divided by 2. And what is my cosine pi t?
X over 3.
X over 3. And so I can just change the order here, and I get x squared over 9 plus, oops, forgot the square there, y squared over 4 equals 1. And so, did we get the equation of an ellipse?
Yes.
Yep, center at 0, 0. What's the x radius? 3, right? Would be the x radius squared. So x radius is 3, y radius is 2, and that's exactly the ellipse that we sketched when we sketched the parametric function. X radius of 3, y radius of 2. So again, this is showing that, so this equation of this ellipse is equivalent to, it's the same set of points as the parametric function that we sketched from the beginning. The x equals 3 cosine pi t, and y equals 2 sine pi t. Any questions on that?
I have a quick question.
Sure thing.
Okay. What are we subtracting x by in the numerator just to be absolutely certain?
Well, this
Because
is the center. This you're talking about this XC and YC?
oh, okay, that makes sense. Thank you. That's
Yeah,
fine.
we didn't have that. In this one, we had the center was 0, 0. So there was nothing to subtract. You could write x minus 0 squared if you wanted and y minus 0 squared. But it's just implied that the center is 0, 0 for this ellipse, like the one. That's the one we got.
Yeah, I just want to make sure I'm like writing them correctly in my notes, and I didn't want to like.
Yeah, so this is just the more generic equation for an ellipse where the whole ellipse could be shifted away from the origin.
Mhm.
And then if you had that, if it was shifted away, then this would just be, your x-coordinate would be then plus xc. And your y-coordinate would be plus yc. And that would shift it away. All your x-coordinates now would be shifted away from the origin by your x-coordinate of your center, and all your y-coordinates would be shifted away by the y-coordinate of the center. But we had plus 0 and plus 0 for ours.
Thank you.
Okay, you're welcome. Other questions? Okay, so let's keep looking at this one. So here is another function. And this one is 3 cosine 4 pi t and 2 sine 4 pi t. Is this the same function or a different function?
Different function.
I have one vote for different. Why different?
Same t, different outputs.
Yeah, right. So for this one, if say t is pi over 2, so if t is pi over 2, my blue function gives me the point, what does the, oh sorry, 1/2. If t is 1/2, my blue function gives me what point? Is that 0, 2? I think. Cosine of pi over 2 is 0. Sine of pi over 2 is 1 times 2 is 2. But my red function gives me what point? If t is 1/2, then this is going to be 2 pi. Cosine of 2 pi is? 1, so that'll be 3. And
Zero.
sine is going to be 0. Right? So it's kind of like, of course they're different functions, right? They have different formulas. So there's a different formula for x and a different formula for y. So, and we see that, you pick a value of t and you get a different resulting ordered pair in each parametric function. So why would I ask this question? Why would I ask, are they same? Of course they're different. You get a different ordered pair for each value of t, and they're clearly different formulas. So why would I ask this question in the first place?
Will they have the same radius in terms of x and y?
Okay, yeah, so look, they have the same x radius, same y radius. What else?
They'll make the same graph, won't they?
Yeah, because look, if you do the Pythagorean identity, you do the cosine squared plus sine squared equals 1, and you have the same argument. And then after that, the t's would go away, and we'd end up with the exact same equation, x squared over 9 plus y squared over 4 equals 1. Both of these will resolve to the same equation when t is eliminated. So, what's the same? The same is they give the same set of points. It's the same ellipse. What's different?
Different orientation.
Okay, different orientation. So what do you mean by that?
They'll be traced in a different direction as t increases.
Okay, well, we get a different direction as t increases. Others, what do you think?
I thought I thought that they would go in the same direction since sine was still bound to the same x and y variables as they were last time.
Okay.
But I'm thinking more along the lines that the ordered pairs, like parametrically, like are like different.
Okay.
But they still trace the overall same shape.
All right. So same set of points in the same direction. Then what's different?
For every value of t, there's a different order.
So like if I were to let t go from 0 to 1/2, what would happen in terms of generating the two curves?
Won't the second graph, the rate is 4 times as fast?
Okay. Right. Yeah. So if t goes from 0 to 1/2, this argument's gonna go from 0 to 2 pi. This argument's going to go from 0 to pi over half, pi over 2. So right, the rate of generation will be 4 times as great, and so we'll get, in just from 0 to 1/2, we'll get a full rotation of the red graph. So there's 0 to 1/4. The 4 pi over t has already made it half of the ellipse, where the blue version has only made it 1/2 of 1/4 of the ellipse. And then if I take t from 0 to 1/2, here's t from 0 to 1/2. The first one has only made it 1/4 of the way, because we've gone from 0 to pi over 2 in the argument. 0 to pi over 2. But the second one, when t goes from 0 to 1/2, the argument makes it all the way to 2 pi, so it makes a full rotation. So by the time you get to t equals 1/2, the red graph is kind of done plotting all of its points. The blue graph is only 1/4 of the way done. And so we have to keep increasing t so the blue graph can finish plotting the points. Okay, so by making a new argument, right? It's the same function with a different argument. So I made this argument 4 times as great as this one. And what's the conclusion? Is it the same function or a different function?
Same function with a different rate.
Okay, I have same function. Is it the same function? Different function, right? You get different ordered pairs for every value of t and a different rate of generation. But what's the same?
Same range.
That produces, right, the same range of values. Range being all the dependent things, right? So then you get the same graph in the end, right? So once t makes it far, once you have enough of the t values put through the function, then you get the same set of points with the same set of ordered pairs. But they're different functions because of how it generates the ordered pairs, right? Different values of t, or the same value of t gets different ordered pairs. Okay, any questions on that? Right, so clearly a different function, but you do the math and you get the same ellipse. Same set of points. Same in the end, you get the same set of points. Okay, so now what if we were given the equation of ellipse and we had to make the parametric function for it? So let's try that. Can I erase? Any more questions on this? So let's look at what I want to do. Let's look at 16x squared plus y squared over 9 equals 1. All right, so let's get that into ellipse form. So we want to get that into, say, x squared over something plus y squared over something equals 1. So it would be x squared over what? Would be the same. 16x squared is the same as x squared over or divided by
1/16.
1/16, right? Okay, so that would give me an ellipse, and my radius in terms of x would be what? And my radius,
1/4.
yeah, 1/4. Then, and my radius in terms of y would be 3, right? So we could sketch that ellipse. It's going to have a center of 0, center 0, 0, x radius of 1/4. So it's going to be like here and here. And a y radius of 3. So I got to zoom out some more here. And so it's centered at 0, 0. Y radius is 3, so we can go 3 from the origin. X radius is 1/4, so go 1/4 on the origin, and I can just try to sketch that. Best ellipse I've drawn all day. But let's make it really pretty. Oops, that's not going to do that. So now I've drawn the, I'll let the software do it, nice and pretty. So the question is, now we want to write the function for this ellipse. As a parametric function, right? As a parametric function. So we could rewrite this ellipse as x over, say, 1/4 squared plus in total, right? So now we could make these ratios a whole ratio squared. Is that okay? Can I do that? So x squared over 1/16 squared is the same as x over 1/4 all squared. Y squared over 9 is y over 3 all squared. That. And then what are we looking at here? What does that look like? Again, the bridge between these equations of x and y for circles and ellipses and our parametric function is the Pythagorean identity. So in the Pythagorean identity, what will be equal to, say, cosine?
Excuse me, x over 1.
Yeah, so I can say that this argument in here is cosine, and this argument in here is sine, and then that would be accurate, because then cosine squared plus sine squared equals 1. And then I can choose my argument too. I could just simply say cosine t. So I could say cosine t equals x over 1/4 and sine t equals y over 3. And then what? So we know our parametric function is what is x? You know, what is x in terms of t? What is y in terms of t? So here x would be what? 1/4 cosine t. And y would be 3 sine t. Based on letting cosine be this inside these parentheses, sine be inside these parentheses. Then we get x equals 1/4 cosine t, y equals sine 3t. And that would be the parametric function for the same ellipse. That this was the equation of x and y for. And so because x is cosine and y is sine at t equals 0, we would be at the right side of the circle at 1/4 0. And as t increases, we would be going around counterclockwise. So this has a starting point of, starts at 0, 1/4, and generates counterclockwise. Just like the basic unit circle where x is cosine and y is sine. Okay, but then doesn't any questions on that? So here's the parametric, here's one parametric function, and then you could have you could choose any argument you want for cosine and sine, just as long as they're the same. So you could choose pi t for both, you could choose pi over 2t for both, you could choose 2 pi t for both, you could choose 8t for both, as long as they're the same. The Pythagorean identity holds, so I just use plain old t, and that's fine. Okay, so notice, looking at this, could I have let x over 1/4 be equal to, say, negative sine t? And y over 3, say, equal to positive cosine t?
Because x and y have ambiguous directions.
Would that still make the Pythagorean identity hold? So now I've got negatives, so that would mean that negative sine t squared plus cosine t squared equals 1. Is it true?
Yeah, because you're basically multiplying that sine t by -1 squared,
Yeah.
which is 1.
Yeah. It works. So there are many assignments of plus or minus sine and plus or minus cosine to these interior expressions here that will still make the Pythagorean identity true. In fact, there are 8 combinations. There are 8 ways to assign plus or minus cosine and plus or minus sine to those expressions inside of the parentheses. 8 ways. Plus or minus cosine of an argument, plus or minus sine of an argument. As long as you have sine in one and cosine in the other, you can have plus or minus on either, and it makes the Pythagorean identity hold, and it will generate the same ellipse. What's the difference in those 8 different choices that you have? You have 4 different starting points, and at each starting point, 2 directions of generation, clockwise and counterclockwise. That's the 8 combinations that result, or that's where you get those 8 different combinations, is from plus or minus sine or plus or minus cosine and then plus or minus the other one that you didn't pick here. That's 8 combinations. So what does this? Where does this one start, and how does it generate? I chose negative sine for this, and positive cosine for this. So what's the starting point for that? So we'll have this function then would be x equals negative 1/4 sine t, and y equals 3 cosine t. So here's another valid parametric function for that same ellipse. Where will we start? At t equals 0, we'll get the point. 0, 0, 3. And then, which way will it generate? So x will decrease from 0 to negative 1/4. Well, y also decreases from 3 to 0, so that will also be, this will start at 0, 3. Oh, this should be 1/4 0. If I make a mistake, please speak up so that people aren't out there being like, I'm not really sure about that. So this should have been 1/4 0, right? Don't hesitate to speak up. All right, so this one starts at 0, 3, and also generates counterclockwise. Because as t increases, your x will go from 0 to negative 1/4. That's your x. And your y will decrease from 0 to 3, so that will also be counterclockwise. If I had chosen negative cosine, then what would that have been? Well, that would have started, then we'd have y equals negative 3 cosine t. We would have started at the bottom, and that would have been actually going clockwise. So had I done x is negative 4 sine t and y is negative 3 cosine t, that would have started at the point down here at the bottom, 0, negative 3. And then x decreasing first, and y would be increasing, and we would be going clockwise. Okay.
So if
Yeah, go ahead.
oh sorry. So if both of them are negative, they would be going
No,
clockwise.
no, you can't make. You had to do each one separately. Don't try to make a rule like that. Do each individual case, work it out. Find the starting point, and then look at your function and let t vary, and see how x and y vary.
Okay.
Don't
thank
try.
you.
Yeah, don't try to make a rule like that. Because here, both of these were positive, and here one was negative and one was positive, and these both went counterclockwise, right? So that just kind of means there's no rule for, you know, both of them being negative or both of them being positive, meaning a certain direction. Okay,